Everybody follow that okay? So again, the only way the red box doesn't slide off of the blue box is if there's a frictional force to keep the red box staying in place with respect to the blue box. This is different than what you did before when we pulled on the blue box. That frictional force tried to prevent the red box from staying into place and the blue box sliding out from underneath it. So the frictional force has to reflect the direction that we're trying to prevent the box from moving. In the case of this one, we're trying to pull the box forward. It wants to slide off of it. Friction is preventing it from sliding off the blue box. Now, Newton's third law says that the force acting on the blue box forward has to be that same frictional force. That's what's causing the blue box to accelerate, is the fact that it's being pulled forward by the frictional force. These two are the Newton's third law pair. There's also weight from the blue box, M1G, normal force from the blue box. There's also a downwards normal force from the red box on the blue box. Probably should differentiate, so I'm gonna put G here, and I'll put B for boxes. These two also constitute a Newton's third law pair. So I'm labeling them correctly. I suspect that all of you already did this, but let's have a combined direction that we call positive. So for everything that's on the table, I'm gonna make to the right positive, and for everything downwards, I'm gonna make that positive. And can we be in agreement that if the red box and blue box don't slip with respect to each other, they will have the same acceleration? All right? And if the string doesn't stretch or anything like that, they will all also have the same linear acceleration. Is that good for you guys? All right, so we're making the claim that the acceleration will be the same all around. All things that we test. Any question about what we've done so far? There's a lot of physicsy things to do next. Let's kind of put them all together. This is a net force equals MA set of relationships. But there's also going to be a net force equals 0 relationship here. Some of that's important and some of it's not. I really don't care about the net force in the y direction acting on the blue box here. There's no friction here, so I don't care about the normal force from the table. So I'm not going to worry about it. If there were friction there, we would need the normal force from the table. However, I do have to worry about the up and down forces here. This normal force is what is basing the frictional force on. So I need to know what that normal force is. So top box first. NB equals M2G. We're going to need that. Friction's based on normal force. In fact, let's get it out of the way. That frictional force has to be related to that normal force. Just dealing with the red box. And finally, it's a whole lot. All right. Any questions about that? Did I do anything weird? Anything outside of our set of steps? Right, so I go to the next box. Deal with the forces acting on it. I only have to worry about the horizontal force, I believe. Yes?
Why isn't it M2A for T?
Oh, it should be M2A. A little bit on autopilot, I guess. All right, next box, the blue box. I only worry about what's happening in the x direction. I don't need the up and down forces. They're not contributing. All right. Anything else about the blue box that's on the table? I don't think so. All right. The blue box that's hung. All right. Any questions? Newton's law and the force concept model gets us here with all of this information. We're trying to figure out what M3 is. And all of this, whenever it's all done, we're gonna have an M3 equals or an M3 greater than or less than something else, right? That's what this ends with. So we want to get M3. There are a variety of things that cannot be in our answer. This 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 and this can't be in our answer. So all the things I'm circling, none of that can be in the answer. You have to find a way to get rid of all of that. And I'll point out, that's a lot of things. And you have 1, 2, 3, 4, 5 equations. I bet there's probably 5 unknowns. Anything that's not circled can be in the answer. Getting to here is obviously critical, because anything after this, if it's wrong, a minus sign out of place is going to make everything else you do wrong. So the procedure just gets you to here. What you do after this, I used to just say it's just math. This is just algebra. This group has proved that that's not enough. So in the past, I wouldn't do what I'm about to do now. But when you look at all of this, anything that's circled, you're going to have to find a way to get rid of it. I mean, you're going to have to find some form of substitution that's going to make it disappear. But ultimately, and you can't lose sight, this is what the problem is about. What you may need to start doing if you want to try and be successful and stop asking me when the retakes are, is understand what you're looking for in these problems. What is the mass that will still keep the system from or still keep the top block from falling off the bottom block? The mass we're talking about is the one that's hung. So at the very end of this, there's got to be an M3 equals or something like that. I'm noticing right away that there's some things I can do right now to start this problem. And because it asked about minimums and maximums, and I know that there's an inequality, I think my goal should be to preserve the inequality. So I'm going to try and do my substitution into the inequality. And with everything I do here, I'm trying to ensure that I get rid of all the things that can't be in my answer. So for example, the very first thing I think, and I'm going to just shift this off to the side, make it a little bit smaller, and I'm going to start doing all the work kind of right over here. And the first thing I noticed is that I can write the frictional force as mu s m2g. That's a substitution. I've gotten rid of one of the variables that can't be in my answer. I have many more to go, but I've gotten rid of one. And I'm noticing I could get rid of fs if I want, but it seems to me that may not work out as well as I'd like. But I could do it. I could write m1a has to be less than or equal to mu s m2g. Unfortunately, that just exchanged one unknown for a different unknown. Except, and hear me out, we've been doing these problems for about a week and a half now. We've been able to realize that in almost every single case with a multi-body problem, you can solve for the acceleration and cancel out internal forces. So finding the acceleration tends to fix that problem. So I see where I can get the acceleration. I see 3 relationships that have acceleration in it. And I've tried to tell you that if you've done this correctly, those 3 relationships, I'm just have to rewrite it. There will be the internal forces canceling out. So I'm going to combine all 3 of these at one time to get a relationship for A, knowing that if I've set it up right, all the internal forces cancel out. And in this case, they do, right? I have a positive tension and a negative tension. Those will cancel out. I have a positive and a negative Fs. Those will cancel out, leaving me with M3G on the left side of the equal sign, and the sum of m1 plus m2 plus m3 times the acceleration on the right side. Every one of these problems always ends up with the acceleration having the sum of the masses somewhere in it. It's kind of how you know if you're doing it right. But remember, net force equals ma. So A is going to be the net force on the system divided by the inertia on the system. Somebody in second period goes, is there a name for the ratio of the unbalanced force versus the mass? I don't really know why they asked me that, but I was looking at this going, yeah, I guess we call it acceleration. No, it's something else. I go, no, I don't think so. But anyways, back to this. Again, not easy, but we've been doing this part a lot. I think finding the acceleration is something you're probably going to have to do. I've made it a part of almost every problem every time, even if it didn't need to be part of the question. I've made you solve for the acceleration. You need to recognize that solving for the acceleration is probably something you're going to have to do to get to your answer, especially if you're solving for a particular force. But now I'm looking at this and noticing everything that's there is allowed to be in my answer, every part of it. So M1 times A, which is a mess. We see it all right? I'd love to say you're done, but that's what you want. Now you have to tease that out of your answer. Now, I see all the things I'm going to have to do. A lot of algebra. Leo, do I have to continue? All right. Is there anybody who wants to see the algebra necessary to tease out M3? Okay. I know I have some students that are having difficulty with these fractions, but I can write this as M1, M3, G on the top, divided by M1 plus M2 plus M3 on the bottom. And that's got to be less than or equal to mu S M2 G. All right. This is going to get messy. So here we go. And I have a never-ending supply of paper. You guys try to cram all this in on the bottom of that piece of paper I gave you, it's never going to fit unless you're micro-printing your answers. So I'm just going to be nice and big, write all the steps out, and I'm going to try not to skip any. But the first thing I'm going to do is multiply both sides by that denominator. I'm going to distribute this term. We know the distributive property, so I just distributed. Any question about that? Yep.
Is that required?
Is that what?
Is that required for like the step before? You have to go there?
You will have to do this because I have an M3 here. It's the only way to tease it out. I also have an M3 here. So I'm going to have to. In fact, so the next thing I'm going to do is move this term with M3 to the other side. God, I really assigned this, didn't I? Hear me out, I didn't make this problem up. I showed you it on the AP exam. You know it's there. I do think I can factor out the M3 here. So let me just shove this to the top again. So I am trying to be careful to do every reasonable step. You have to ask yourself an important question here. There's a a gateway piece of information here. First, this can't be 0, or I can't divide both sides by it. If it's negative, I have to flip my inequality, right? So for the time being, I'm going to say it's positive. But there is the possibility that it could be negative. You'll find if it is negative, the answer won't make any sense. So we're going to leave it and assume this is positive. This is, of course, the weight of the bottom box, which is weird that it shows up. But it's there. This is the the static frictional force, the maximum value it can be. So M3 has to be less than or equal to mu s M1 M2 G plus mu s M2 squared G divided by M1 G minus mu s M2 G. I'd say this is the answer. It has all the things in it that are allowed to be in it. And if you stopped here, you would get full credit. So that was the algebra. So ultimately, I would give anybody who came up with this full credit, but let's face it, that just looks like a nightmare. But it's nice that you know that you could have canceled the G's out. So in this problem, you had to first show something, about this system. You had to find out what angle would the system stay at rest. I think that's what it was, right? So I have this stuff. And we have a pulley, and it's connected to another mass. And what are they labeled? It's like MA and MB?
Yeah.
I don't know which is which.
The one on the incline is MA.
Okay. All right, so this is B and this is A. Angle theta. Did you find that mg sine theta minus tension equals 0, and that this is MA, and MBG minus tension equals 0? This is Newton's first law problem. Eliminate the two tensions and find that MAG sine theta equals MBG. So you cancel out the G's, and sine theta is the ratio of MB over MA. All right. There's some clear implications here. B can't be greater than A. I'm telling you this because you guys don't think like this. At least somebody told me yesterday. I never would have thought of that. Why not? The ratio of sine can never be greater than 1. It's a number between 0 and 1. So MB can't be greater than A. You should know that right away. This is a true statement, and you should know it. Keep it in mind. These problems about always have something at the end. What's a condition that can't exist? That's a situation that can't exist. How do I know it? The same reason you're supposed to know it. Sine can't be greater than 1. Follow me so far? Also, if theta is 90 degrees, it's just a regular Atwood machine because both things are right on either side of the pulley. That's what 90 degrees would mean, right? If you increase this to 90 degrees. Now, it says, will increasing or decreasing this angle cause MB to fall toward the ground? Now, a simple answer is, if you make theta smaller and you leave MA the same, the only way this ratio works is if MB gets smaller, right? When sine gets smaller, the ratio gets smaller. If MB doesn't get smaller, then this is going to be unbalanced. The system's going to move. Is that a reasonable explanation? It uses what you already solved for it. There's other ways you could do it, but that's the explanation I gave.
So will we put that in words? Will we describe that in words? It says, like, how would you show that mathematically? We would just say that.
Well, you could, if you want, I mean, to me, this is partially what's showing it mathematically. Now, there's other ways you could show it mathematically. You could unbalance these. And show that, we could do it right now. I'll do it. Let's show that the mathematics, but to do this, I have to link up my positive directions, which I have not done. So let me link up my positive directions. That makes me switch this one. When they were equal to 0, I didn't worry about the positive direction being in the same direction. But now that the acceleration is being brought up, I have to get my accelerations right. So this is my new relationship. That good? All right, so I'm gonna add those two equations together and get MBG minus MAG sine theta. I'm adding this and this together equals MA plus MB times the acceleration. I'm trying to prove that it accelerates. So I think if I want to make a comparison, I solve this for sine theta. That will help me make a comparison, right? All right. So let's make the comparison. A is positive, and the only way A can be positive is if this is greater than this. Let's keep that in the back of our mind. But I want to get MA by itself, or sine theta by itself. And no, I would not expect you to do all of this on a test, just so we have an understanding. Now what am I doing? That's plus. I'm going to move this over to the other side. All good? All right. I'm running out of space, so I'm just going to do that all up here. I'm going to divide both sides by MAG. First, if the acceleration is 0, we get sine theta equals, right? You guys all see that? So, if the acceleration's not 0, and if positive is down, you guys saw that, right? In the picture, we made positive down here. Everybody follow? Look, the angle has to be less. I'm taking what I had, that's this, and I'm subtracting something from the numerator. That makes the top of that fraction smaller. The angle has to be smaller. That's proving it mathematically all the way. I think we probably didn't have to do all of that to justify your reasoning. I probably wouldn't say prove it mathematically on the test if I was writing the test, and if College Board, they would probably just say justify your answer. Okay? But it can be proven. So just let you know, I would not ask that of you tomorrow. But it can be proven. I mean, math does that. Math proves things. But that's probably a lot to ask of you. Yep.
On this.
Okay, so we're looking for the acceleration of the system. There's a coefficient of kinetic friction here, and we're looking for a mass MB that is slightly bigger than the maximum mass that would have held the system in place under static friction. So the system is accelerating, and I think this is the direction of the acceleration, so I'm going to make that the positive direction. All good? All right. Very little changes for the mass that is hung. It's still going to be MBG minus tension, but it's going to equal MBA. So I don't think I have to redo that one. The one on the table has more forces acting on it. And because I have people that still can't draw a free body diagram, normal, tension, kinetic friction, and weight. All good? Look, we're at the late stage of this. MAG cosine theta this way, MAG sine theta that way. I still see people who can't do this. I don't know what to say. Okay? I don't. So, looks to me like we have MAG cosine theta equals the normal force. We've done that so many times, I feel like I can cut a few of these corners out. And then, since up the ramp is positive, I have tension minus mg sine theta minus kinetic friction equals MAA. Any question about where any of that came from? We sure? So there's not going to be questions tonight at 9:30 about where this came from? Good. Kinetic friction equals mu times the normal force. So kinetic friction equals mu MAG cosine theta. Again, we've done that an awful lot. So all you have to do now is add these two things together after substitution and solve for A. That is perfectly reasonable for tomorrow. Folks, I'll continue to write the answer out for those of you who need it. I see your signature form, but I'm going to see you all day, right? Is that okay? Just do it later? Thanks. Bye, have a good day. Yeah?
Did you record the homework? Are you gonna be able to post them on YouTube today at some point?
Oh, I'm sure I'll be able to post them.
Okay, thank you.
You're welcome. Yes, I do not want to buy your chocolate.
I was gonna give you one if you want.
I don't really eat that. So, I understand that the force is now on the top block, but the system is supposed to be accelerating together. So, I have, let's get a good picture here. I have the top block, or sorry, the bottom block and the top block. And I think they're labeled so that this is number 2 and this is number 1. There is an external applied force here. All right. The problem stipulates pretty clearly that these two things are to accelerate together. So I think we can establish that they will both have the same acceleration. In addition to that, we are told that we want to find the maximum value of this force that can allow the system to accelerate without the blocks separating, and that there is a coefficient of static friction, μs, between the top box and the bottom box, but there is no friction between the bottom box and the ground. So, now, you have a sequence of steps that can get you just so far. Maybe not all the way through the problem, but they can get you just so far. For example, I think we can all agree this is a net force equals MA problem, right? We are told the system's going to accelerate. Even if we weren't, there's good reasons to believe it will accelerate. There's no friction on the bottom box, and we're asked to figure out what the maximum force would be that would allow the two boxes to accelerate together. Tons of clear clues that this is a Newton's second law problem. What we don't want is we don't want box 2 to break friction with box 1. That's what we don't want. But that doesn't change that this is the arrangement. So I'm going to start by a free body diagram. I don't know that it's super needed, but I think we probably need, I think probably wouldn't be a bad idea. So I'm going to do a free body diagram for the top box. I know it's going to be experiencing this external sideways force. I'm just going to call F. And there's some easy ones here. It's also going to have weight. Normal force. And I'm going to put normal force for with a B next to it to remind me this is normal force between the boxes. It's also experiencing friction. There's a frictional force this way. This frictional force is to prevent the red box from sliding past the blue box. Yeah.
If it's not supposed to be moving, wouldn't they be the same length there? Like,
No, because they are. It's not moving with respect to the blue box, but it's moving with respect to the table. So there's an unbalanced force on the box to get it to accelerate. That's a good question, though, and I think that's part of the problem is we see ourselves moving along with the boxes, but we are in a reference frame that is not moving with respect to the two boxes, and we're watching them pass by. You see the difference on how you have to kind of perceive that, I think? Maybe you don't see the difference, but the blue box, let's hit those forces, right? I think right away there is a Newton's third law of force. It says there has to be a frictional force pushing on that box to the right. That is the only way the bottom box moves, is if there's a frictional force accelerating it to the right. It's the only thing that pushes on that box to the right. And this is our Newton's third law pair here. They must be equal and opposite. There's another Newton's third law pair acting on the blue box, and that's that normal force. The upwards normal force from the blue box onto the red box has to be equal and opposite from the red box acting downwards on the blue box. Although I don't know how important these forces are, these up and down forces. Because there's also going to be M1G and also some probably pretty large normal force that's going to go off the screen there. This normal force only matters in this problem if there's friction on the table. If there's no friction on the table, this normal force isn't going to play much of a role in the problem. But keep in mind, just because we're throwing it out, not worrying about it, if there was friction there, you may have to take it into account. This is it. These are all the forces acting in the system. So we begin now by applying Newton's second law and maybe Newton's first law when necessary. Let's talk about the red box first. In the x direction, I have F minus the frictional force equals M2A. Go ahead.
With the blue box, instead of like putting the normal force down, can you say the weight of the second box?
They are equal, and you will find that to be equal due to Newton's first law. But if you're labeling the diagram, I would put it as a normal force because it's not the weight of that box. I mean, it will be that same size, and I get why you'd want to do that. But for all intents and purposes, if they want to be very particular, they may not give you that point. Now, at the same time, net force in the y direction is necessary here because we're dealing with friction, and this friction comes from this normal force. So I'm going to say that NB equals M2G. The net force in the y direction equals 0. The last thing I need to add here is that we have friction. It is very likely we're going to need to use our expression for friction. That's it. That's all we can get from the red box. But this is what the force concept model produces for us for the red box. For the blue box, I'm only going to worry about one of these, I think. And that is that the static friction causes the blue box to accelerate. I could do the y direction as well. I just don't think it's going to contribute to the problem. We're never going to need this normal force because there's no friction here. Now, if it was a different problem where that normal force might be necessary, we could get it out. And if you're desperate for it, we can write it in there. I just think it's going to be more distracting than it is helpful. So I'm going to leave it out for the next portion of our discussion. But somebody said to me, I get all of these equations. I'm not sure what to do with them all. I understand that, because if you did write it in, you'd have this other formula. That's a lot of formulas. And that's all it did was, Newton's laws get you here. So now what? Right? We got all of this. What do you want? It might be difficult for you to even understand, what am I supposed to do with all of this information? Here's where I want to maybe add to my discussion. I didn't think that this would be the problem I would have this year, but it seems to be. Your problem asked for this. You want that. That's your answer. Solve for it. But you can't have this in your answer or this in your answer. You can't have this in your answer. You can't have these in your answer. And you can't have this in your answer. And you can't have this in your answer. And you can't have this in your answer. And you can't have that in your answer. None of those can appear in your answer. Everything else can. But none of those can appear in your answer. So let's say you start by saying, well, I'll solve this for f. Great. Now you better start getting rid of the other things that are there, because the other things that are there can't be in your answer. I'm doing this just to let you know this is what your job is now. You need to find this, this force. This is the one you're looking for. All the things I didn't circle, they can be in your answer. There are some things that work better than others. One of the things that works better here is to find the acceleration. Finding the acceleration will immediately cancel out internal forces and help you. So I would do that. I would try and get rid of whatever internal forces you can to get an expression for the acceleration. So that's what I'm going to do. I'm going to take these two functions and add them together and get an expression for the acceleration. Now, I'm just giving you hints. That usually gets you something that's useful. Doesn't always, but it usually gets you something that's useful. In this case, it gets me this. That's what it gets me. It gets me an expression for the acceleration. I could solve that for A. All of that can be in my answer. In fact, I want F. I'm looking for F. But these things can be in my answer. These are good things. I guess if I sub this into another function, they're good. But now what? There are some clues as to what to do next. The problem asks for the maximum force. And we know that this problem is about static friction. There's probably no way you can get this problem done without dealing with this. Right? It's got to have to do something with static friction. So the equation for static friction is very likely to make an appearance. Well, let's make an appearance now. We know some things about static friction, meaning we know this term, it's here. And it's in terms that we're allowed to have in our answer. In fact, we have a couple ways we could substitute in for this. One of them has something we're allowed to have in our answer and the acceleration, which we just put together. I'm thinking that's the way to go, to sub into my inequality as best as I can. And I've used that phrasing a lot, substitute into my inequality. So that's where I'm going to go next. For Fs, I'm going to choose this M1A. That's got to be less than or equal to, so that's what I'm doing right there. Mus times the normal force, well, I have that right here, M2G. Now I think I have something that's useful. Moreover, I think I see a pathway to get the applied force in terms of everything else that was given. Because if I do this substitution, I will have eliminated everything that can't be in my answer and have left it in terms of stuff that can be in my answer. So M1 times F divided by M1 plus M2 less than or equal to mu S M2 G. Our job is to solve for F. So, and I've looked at some of your work. I went through some of the homeworks. Algebra's tough for us. So I'm gonna be more explicit than I normally would today and do things a little bit at a time. I'm gonna divide both sides by M1. M1 has to be a positive number, so my inequality won't change. I am gonna move the M2 out front and divide it out by M1 and just regroup this a little bit. Now I'm going to multiply by M1 plus M2. And that's it. That's the answer. Yeah?
Why did you move the mu static G out?
You mean, why didn't I just write this over here?
No, like, when you divide over the M1, wouldn't you have to put it under the other half of that equation too?
This and this are the same. The reason why I want it like this is I like the fact that this ratio is here. This ratio to me is important. It tells me something about the ratio of M2 to M1 determining how much force I can apply. If M2 is getting bigger compared to M1, I can apply more and more force. Does that make sense to any of you? Because that means the top box is getting heavier compared to the bottom box. That means the friction is going up because there's more normal force between the two boxes. More frictional force means I can probably push harder without those boxes separating. Having this out front, that makes perfect sense. The whole acceleration is based on the whole mass of the system. Having that sum in there doesn't surprise me. The more inertia it has, the less it accelerates, probably the more force I can apply, and that's clearly evident there. Stickier surfaces mean more force. Does that make sense to have that in the numerator? Sure does. Gravity being here, well, that's what creates this normal force in the first place. Without it, I wouldn't have to worry about it, right? There's no gravity, there's no frictional force at all. This would never work. So the reasons that they are all there are good. Also, less than or equal to means that this is a maximum when they are equal. So having inequality helps me support that I was looking for a maximum. All right. And what's already here, and when I say already here, let me go back to where we're talking about. Get rid of all of this because I don't need any of that. I know I'm not going to need the y stuff, so I'm going to get rid of that if that's okay. We're not talking about F max anymore. We're talking about the fact that there is a tension acting on the system. It's over there now. That changes that value of F to a value of T. Right? The tension force. But I'm creating this T to serve a function, the tension in the cable. I'm talking to Gabby when I say it. So T can't be in my answer. So let's get that right out of the way first. All of the other forces are going to still appear here in the same way that they were there. Everybody understand that? The difference now is that, in our new problem, we have a pulley and this is attached to a string. And at the bottom of the string is yet another box called M3. And this box is now causing the system to move. That okay? I know it's kind of a convoluted drawing. I just wanted to get it shoehorned in there. Everything about the red and blue box stays the same. None of that's any different. But now the thing that's actually the external force is this tension. So I'm going to extend what I call positive to include that box now. And I'm going to add to this set of functions the free body diagram that describes the forces on box 3, of which I think there are only 2 forces. M3G and tension. And now we have an additional hanging box. And that hanging box has a function of M3G minus T equals M3A. All the A's are the same still. However, A can't be in my answer, T can't be in my answer. I'm looking for M3. That's what I want. I want M3. So from this point forward, the functions are changing a little bit. We want to find M3. I can reuse most of this stuff, but clearly my acceleration is now different because these 3 functions contribute to the acceleration. I would recommend finding the acceleration first, just like I recommended before. So that's what I'm going to do first. I'm going to add those 3 functions together. It's a little messy, and I'm sure that I don't have to do this for most of you, but for a few of you, probably taking a bit of a reset and just rewriting this out will help a few of you get caught up, because you can't just erase everything and redo. But these are the 3 functions that contribute to finding the acceleration. So I put them together. We still have Fs is less than or equal to μs times the normal force between the boxes. And we still have the normal force between the boxes is equal to m2g. And I believe that's all we're going to need to solve this problem. So I think, yeah, that's it. So I'm just going to move all that out of the way. We'll focus on these. Is that good for you guys? All right. First thing I'm going to do is get an expression for the acceleration by adding all of these 3 things together, noting that the frictional force cancels and the tension cancels. You guys see that all right? This shouldn't be too crazy, because what it gives you is M3G on this side, the one thing that's causing the system to move, equals all of the masses times the acceleration. Every time you do one of these problems, you should see this appear in the problem somewhere, and here's where it appears here. The one lone thing that we hung off the edge is the only reason the system accelerates. How much it accelerates depends on the inertia of the system. I'm probably going to need this later, so I might as well solve for the acceleration. I'm going to remind myself that I'm looking for M3, and I want the smallest value for M3, or the largest value for M3, that will allow the system to accelerate without the top mass sliding off the bottom mass. So that the fact that it's a max-min problem, inequality is probably a good place to start again. So I'm going to use the inequality. I'm going to make some substitutions. First substitution is going to be these 2. Get rid of that NB, get rid of that friction. Now, we've already done this once, but what we have to sub in for the acceleration is a little bit more cumbersome. I guess that's the nicest way to say it, but I'll go ahead and sub it in. And this is just messy. All right, so we've done it. By we, I mean I've done it, but you were there. Your excellent moral support. we have a function that has nothing but things that can be in our answer. And one of the things that's in there is M3. We need to solve for M3. The problem is that M3 appears 2 places. We got to tease it out and get it in one place. We need M3 equals or is less than or is more than something else. But that's just algebra. So if you're comfortable in your algebra, we can just stop right here. But if you're not comfortable with your algebra, then I have to continue. I'll leave it to you. How would you like me to proceed? Yeah, are you good here, or do you want me to continue? Continue? All right. I was asked last night, was I always good at doing this stuff? No. I was just like you guys. I had to practice, and I made mistakes, and I screwed up my algebra all the time. And I got tired and did my homework late at night, just like you guys. The only difference is that I've been doing this for 30 years in a row. I better be good at my algebra, right? If for no other reason than if I'm bad at my algebra, you guys won't trust me. All right, so again, I think that there are things that I'm going to do here that you guys don't know to do, but the first is I'm just going to write this up here so I have a clear fraction. I wouldn't normally do this, but I'm doing more steps than I normally do, just so that people who are having difficulty with the algebra can see them. There's nothing really for me to do over here to make this easier, so I've done that. I'm going to multiply both sides of this equation by what's in the denominator here. I'm trying to tease out M3, and all those things are being added together. There's no other way for me to get M3 by itself unless I can get that out from underneath the denominator. So normally I would do my distributive property at the same time, but I found in third period I needed to break that up into 2 steps. So I multiplied it, got it on both sides. I'm still trying to tease out the M3. I can't do that until I distribute. So I'm going to just use the distributive property now. All right. Okay, again, I'll say just algebra, which is all it is. But yeah, there's a lot to write there. You have to be careful. Notice, I'm not skimping on steps and I'm wasting the paper. I'm not trying to cram it into the bottom right-hand corner where the page number is or something, like you guys tend to do, as if the paper's is magical and there's not another sheet ever again. Just grab another freaking sheet already. Because if you're getting your algebra wrong because you're too scared to use another piece of paper, you understand how ridiculous you look? Just grab another piece of paper. I have stacks of it. I'll give you some. I want to take this away from both sides so the M3 is on the same side. So much. All right. I have 2 terms with M3 in it now, so I must factor out the M3. The fact that you're likely to only get 1 point for doing all this should tell you that there's not as much value given to this as you would probably like, but at the same time, it could be 2 points. It's hard to know. I factored out the M3. Everything on this side stays the same, although I would probably start looking at factoring out some stuff over here too, but so now I just have to divide. Be careful, this should come up. If this were negative and I divide both sides, then I'd have to flip my sign. But if it were negative, it would mean that the mass had to be negative, right? Because this is positive for sure. Do you understand what I'm saying? The only way the right side of this can be positive without this mass being negative is if everything in here were positive. I'm just doing the thought connection necessary to say I'm not going to flip the inequality. The This is all math stuff, but these are the kind of things that we have to think about. So I'm going to go with what I have here and divide out by that, and I get M3 is less than or equal to mu s m1 m2 g plus mu s m2 squared g, all divided by m1 g minus mu s m2 g. Eek. That's the answer. It's a less than or equal to, so we're talking about a maximum. You may not know why I'm doing what I'm doing right now, and I don't care. I'm doing it because I think it's interesting. You don't have to understand why I think it's interesting. If you look around that fraction, the size of the frictional force shows up in a couple places. It kind of controls this whole problem. And it's got to be true. It's the frictional force that shows up everywhere because it does control the problem. There's interesting things about this, but you might not see it, like the fact that the sum of the masses contributes to how much mass I can have hanging off the table. If the stuff on the table is more massive, I can have something off the table that's more massive. That's what that says right there. I'll also point out in an interesting quirk, there's a value, there's a G in every single term. The truth is, we could get rid of G. In every single term, it's there. The weird thing is, without G, this problem doesn't even work, right? There's no gravity to pull down the weight off the table, and there's no gravity to cause there to be friction. So the truth is, without G, there is no problem. But the fact that it doesn't contribute to the answer, that's a little interesting. A little interesting. You may not see it as interesting, but I do. The top is mass squared. The bottom is mass. So that suggests that my answer will be a mass, which is what I want. So if we do this the long way, and since we have shortness of time here, I'm going to make this the positive direction. And I'm going to say pretty clearly that they both have the same acceleration. That's going to make 2mg minus tension equals 2ma. I didn't draw a free body diagram, but are we okay with that? Your free body diagram would have to have the following characteristics. Weight over here greater than tension. Weight over here, half the size of the weight over there. And the tensions would have to be the same size, but tension on this side bigger than the weight on this side. Tension on this side smaller than the weight on this side. That's what I'd be looking for, but I would give you a grid so you would have a way to line those up and make sure that it conformed to those ideas. This side I'm going to get tension minus weight equals ma.
Is it the same tension on both sides?
Has to be if it's a massless pulley. So we move on to the next part of this, which is let's figure out the acceleration. Bring those two things together, add them up, and I get 2mg minus mg equals 2ma plus ma. So mg equals 3ma. So the acceleration is a third of g. I know I'm going fast, but I also want to finish this before the bell rings. Keep going. Okay. So that's part A. Part B is to find the tension in the string. So it doesn't matter which one of these I choose for the tension in the string. I'm going to use this one to find the tension in the string. So T minus mg equals ma. It looks like the tension equals 4/3 m. I'm sorry, not 1/3 ma, 1/3 mg. There. So it looks like the tension equals 4/3 mg. That good? Now let's test that. 4/3 mg is less than 2 mg, so it definitely fits that one. And 4/3 mg is greater than mg, so it fits on that one. This is a tension that's between the two values, and we knew it needed to be between the two values, right? It had to be lighter than the box on the right and heavier than the box on the left. Question C asks, what is the normal force from the table on the apparatus. The apparatus is experiencing 4 forces. 5 mg downwards, normal force upwards, and 2 tensions downwards. Good so far? So normal equals 2 tensions plus 5 mg, because the net force on the apparatus is 0. Well, the tension is 4/3 mg, so that's 8/3 mg plus 5 mg. But 5 is 15/3. So 15/3 plus 8/3 is 23/3 mg. It's important because 24/3 would be 8 mg. 23/3 is less. It's 7 2/3 mg. So the table doesn't provide the support for all the masses. It provides less because the entire mass of the system is 8 mg. But part of that system is accelerating downwards. If I was to provide you all right over there? Don't fall asleep. That's only in 5th period. I only have 2 kids. They're allowed to fall asleep. No one in this class better fall asleep or you get a pencil in the eye. The upward force from the table is less than the weight of the apparatus because the apparatus is accelerating downwards. There is a mass, 2m, accelerating downwards. So the system is not at rest. The center of mass of this system is accelerating, and it's accelerating downwards. That's why the table doesn't have to support the full weight of the system. And we proved it. I mean, that's how much it supports. You only need the 3rd question answered? Anybody need to see anything else besides that? So I can start there? All right. So I'm going to take a moment just to draw it out. This one's 2m, and the whole apparatus that supports it is 5m. You guys said you don't need to review it, so that means you know that the acceleration is 1/3 g, and the tension in the cable is 4/3 mg. So I assume you have no questions about where those came from because nobody asked about it. The table is applying an upwards force on the apparatus, a normal force. But there are 2 other forces acting on the apparatus. There is the weight of the apparatus, 5 mg, and then 2 tension forces. But the apparatus is at rest. It doesn't include the 2 boxes, it just includes the apparatus. It's at rest, so the net force on the apparatus is 0. Okay? So normal equals 2t plus 5 mg. Well, the tension is 4/3 mg, so normal equals 8/3 mg plus 5 mg. But 5 mg is 15/3 mg. So this gives me a total of 23/3 mg. And that's clearly less than 8 mg, as I indicated in the problem. there's a perfectly reasonable explanation as to why. You should be able to explain it. By the way, 23 thirds is 7 2/3 mg. So, why is it less than 8 mg?
Because it's also accelerating afterwards almost.
The apparatus is not accelerating.
And the tension is going up.
I mean, because if you were to have to explain this, you know, you would need a way of, I mean, we can calculate it, but asking why it's less and being able to talk about that in plain language might be tough. It doesn't have to support these two weights. It has to support some of it, but not all of it, because those two weights are not stationary, they're accelerating. One of them is accelerating downwards and one of them is accelerating upwards, but more weight is accelerating downwards than upwards. So the net effect is that the mass of this whole system is slowly accelerating downwards. And so the upward force doesn't have to equal the weight of the system because some of the system is accelerating downwards. Let's handle the straightforward things. We are trying to figure out the maximum size of this box that will allow the system to accelerate but not have box 2 separate from box 1. And again, we've already done part of this problem if you did the one right before this. This one, though, is the coup de grace, right? This is the full Monty. There's all sorts of stuff here. So there are 3 objects here. They're all accelerating at the same rate. And I'm going to choose this as my positive direction, and I'm going to say they all accelerate at the same rate. I don't know how warranted a free body diagram is, but probably best that we do one anyways. So I have the green box, the blue box, and the red box. All of these are going to have a free body diagram. Let's start with the green box. It's one of the easier ones. There's just 2 forces acting on it. M3G. Tension. I'm conscious to make the tension less than M3G. Now let's go to the red box since they are connected together. Tension, trying to make it the same size as the tension that's on the green box. And M2G, normal force. And static friction. Static friction is trying to prevent one surface from sliding past another. If the blue box doesn't move, this is the direction of the frictional force on the red box. Everybody understand? Even if the blue box does move, this is the direction of the frictional force on the red box. Lastly, and I'm going to put a little B here for normal force from the box, because the blue box also is experiencing a frictional force this way. These are a Newton's third law pair. It's got its own weight, M1G. It's got a normal force from the table, but I have to make that kind of big. In fact, it extends further than we can see because there's also a downward force from the box before it, normal force from that box. Good? Third law pair, third law pair, third law pair. All right. So ready to move on? We can generate a relationship to describe the motion of each of these boxes by using Newton's first and second law for each set of things that we have here. I'm going to start with, I don't care, how about the blue box since it's all the way in the upper left-hand corner? I am not going to worry about the up and down forces. I don't think the box is accelerating up or down. I think the box is only accelerating to the side. Would you agree with that assessment? All right. So on that box, I'll have Fs equals M1A. Good for you?
Yep.
Great. Yersa, tell me why I don't have to worry about the up and down forces here. Because you're clearly confident. Yeah, tell me why I don't have, I'm sorry. Tell me why I don't have to worry about the up and down forces on this box. This one right here. Please. Why? Why don't you want to tell me? Okay. Are you prepared for tomorrow? Okay. So, there's no friction between block 1 and the table. So I don't really think the up and down forces matter there because normal force from the table would contribute to frictional force from the table. But I don't want to have to, I mean, I could write it all out, but I think it's just going to be distracting. So that's why I'm not going to write that one out. I do care about it accelerating to the right. Is that good? All right. The red block, I'm going to have T minus F of S equals M2A. Is that good for you? All right. I do think I have to worry about the up and down forces from this block because it's this normal force that creates the frictional force. So the net force up and down is equal to 0. So I'm just going to have NB equals M2G. That good? All right. Last is the green box, and there's only the two forces acting on it. So M3G minus tension equals M3A. All right, so I've used all of Newton's laws to generate the relationships that are there. There's one more thing I probably should put in here. We're dealing with friction, so I don't think it's a surprise that we're probably going to need that static friction is less than or equal to mu s times the normal force. I think that's going to come into play. All right, that's what the force concept model can do for us. It doesn't solve it. In fact, the first thing I want to point out, and this was actually a question from 6th period that I think was good. What can and can't be used in our answer? Well, the only thing that can actually be in our answer are the masses, the coefficient, and any fundamental constants. But somebody in 6th period goes, well, why can't I have anything else in my answer? Well, in this problem, unless, I mean, if they didn't explicitly tell us what can be our answer, any variable name that we made up can't be in your answer. You made up a construct that's not part of the problem. I made this variable up, right? It's friction. It's not given to me. I had to know it was there, but I made it up. It can't be in my answer, so any appearance of it can't be in my answer. Acceleration is clearly a part of this, but again, it can't be a part of my answer. Tension, again, I made that up. It's a construct. It's something I introduced into the problem. It can't be in my answer. Normal force, same thing. It can't be in my answer. Anything that is circled here can't be in the answer. But the answer is to find M3. I need to solve this for M3. So I need an expression for M3 that can be in terms of everything else, but none of the circled variables. I think that's where we've had some challenges, is I'm not sure what to do next. Well, that's what's to do next, is to try and figure out how to get M3 by itself on one side of the equation and everything else on the other side of the equation, but without having any of those circled variables in your answer. There are some things you can do straight away that will assist you in this task. The first one is finding an expression for the acceleration. That will assist you in this task. I would highly encourage you to do that first, because we've done this a couple of times now. In any multi-body problem, if you add up all these equations, your internal forces will disappear. And that's a good way of getting a new expression that removes some of those circled variables. So for example, if I, at this moment, let's just get rid of all those circles for a minute. If I add up everything in these three equations, this set of forces will cancel out. They'll add to be 0. And this set of forces will add to be 0. And that leaves me with just M3G on that side of the relationship. The other side, the sum of all the masses. Now, this gives you something that is probably going to be useful later. It gives you an expression where everything in that expression is something that can be part of my answer. I have a way of getting rid of acceleration if it shows up later with everything that can be in my answer. That's a good start. Although acceleration isn't what I'm being asked, it might show up later. So next, where do I go next? Well, to be honest, I don't think they would have given us the coefficient of friction if it wasn't going to be used. Now that's not a dead giveaway, but isn't it pretty clear that the coefficient of friction controls how much frictional force there is? And this whole problem hinges on us not breaking the frictional force. So I bet using this is a good call. So I'm going to use that next. And the reason I wanted to pick that one is because I have an expression for the normal force that has things in it I'm allowed to have in my answer. I also have a very simple expression for the frictional force that has something in it that can be in my answer and acceleration, which I just showed. I have an expression for that has all things in it that I'm allowed to have. I think that's where to go next. So that's where I am going to go next. I'm going to sub in for the frictional force. And now I'm going to sub in for the acceleration. And that's the answer. I mean, you won't get credit for it. But this is an expression that has everything in it that's allowed to be in my answer. All I have to do now is tease out M3. Now, I'm not saying that part's easy, but I think it's something that's achievable. So this is this part right here. This is what the force concept model gives you. This, I think, is utilizing our knowledge of how to deal with Newton's laws for a system. This part, reasoning out what you have to do to get rid of variables that are not allowed to be in your answer. These are probably all going to have points associated with each of them, but probably what you have to do next, getting M3 out of this, is probably just worth 1 point. It's just algebra. So I'll leave it to you to decide whether you need me to continue. You're good? Anybody else need me to continue from here to get M3 teased out? We're good? All right. One correctly. So I'm assuming you did number 1 correctly. You got this as your expression. So when M1 is much greater than M2. So when M1 is much greater than M2, this term goes to 0. Do you see that? If not, make M2 1 and M1 a million, a billion. Make it big. Infinity doesn't have to be that big. It can be a gallon jug compared to a paper clip, right? So in this, you understand that the top is 1, and the bottom's 1,000,001, right? That might as well be 0 when we multiply that by 10. You good with that?
Yeah.
All right. I'm sorry, let me back up just a little bit. When I read the question, it wants the minimum mass of MB that will prevent MA from sliding down the ramp. So again, when we draw the free body diagram, I want to consider that we're trying to find what will prevent it from going down the ramp. So this is a net force equals 0 problem. We should consider direction even though it's a net force equals 0 problem. even though it's not going to matter that much. But I know in the next question, it says assume the mass is slightly smaller than what you found in part A. What is an expression for the acceleration of the system? So in order to be consistent between part A and part B, so I can reuse some work, I'm going to make this the positive direction, because in part B, it's going to accelerate that way, or at least I think it will. Does that make sense? So I'm just looking for some consistency. And I think in part B, the acceleration will be the same for both masses. But part A is a net force equals 0 problem. I'm just trying to set myself up for better success for the next portion. I have weight downwards. This is MAG. I have normal force upwards. I have tension perpendicular to the normal force this way. Although I'm not so sure I did a great job with perpendicular. And I must have friction also going this way, and this is static friction. Trying to prevent the box from going down the ramp. Now mg is going to be broken up into its components, so there's going to be a mg cosine theta and an mg sine theta. So this is not a great free body diagram. You should do better. But the free body diagram wasn't actually required in the problem. It's just a construct for me. The box that's hanging off the table, two forces, tension, and MBG. All good? Tension is a Newton's third law force between these two. It'll be the same value in both. So tension minus MBG equals 0. mg sine theta, it's MA, I'm sorry, I should put all the A's on this. So MAG sine theta minus static friction minus tension equals equals 0. This is the 0 part. There we go. And let's see. I am going to need a normal force, so let's do that part. Normal equals MAG cosine theta. All right, there we go. That's Newton's laws. They did all of that. I don't think it's complete unless we consider the fact that this is a static friction problem. So I've got all the pieces left. Again, this one's not accelerating. We are interested in this, right over there. We want MB equals something. In that, this can't be in the answer. This can't be in the answer. This can't be in the answer. That can't be in the answer. That can't be in the answer. That can't be in the answer. None of those things can be in the answer. So I want to get MB equals something, but I can't have any of the stuff that's circled in red in the answer, so I need to get rid of it all. Since this is a pretty standard inclined plane question, one of the first things I notice is I could probably do a bunch of quick substitutions, but it's a static friction one, so I want to sub into my static friction formula because that's where my inequality is. So I see a pathway to do that. For example, I see that I could solve this for tension and immediately put tension here. Then I could solve that for friction and immediately put friction there. The pathway, right? That'll eliminate tension and will eliminate friction. And all I have left to eliminate now is the normal force, and I can do that here. That good? All right, so that's what I'm going to do. First, I get that Fs equals MAG sine theta. I'm just taking this one and doing my algebra. I moved Fs to the other side, minus tension, which is MBG. There we go. So that's what I'm going to use for my frictional force. And then I already have it solved for my normal force, so let's put them together. That has to be less than or equal to mu s times MAG cosine theta. So done all the math. or at least all the physics part of the math. Now I just have to isolate MB. I'm going to move MB to the other side of the inequality and move the MAG cosine theta to the other side. So I'll get MAG sine theta minus mu s MAG cosine theta has to be less than or equal to MBG. I have a G in every term. That's my answer. And it says MB has to be greater than or equal to. So this is already telling me that there is a minimum. The minimum occurs when MB is equal to that expression. Good to go? All right. So now we have the situation in which MB is actually less than that. Okay? Now, luckily for us, we had a little foresight, so we don't have to do as much work redoing this problem, but we do have to redo this problem. The system's going to accelerate now. So this is not a net force equals 0 problem. This is a net force equals MA problem. But also, we have broken static friction. So we're not going to have an inequality now, we're going to have an equality, but we have to change that to be K over here. So this is K, this is mu K. Let's see, what else? Any place where I had net force equal to 0, I have to put net force equals to MA. And any result that came from that. So all that's got to go and all that's got to go. So this is going to equal MBA. And this is going to equal MAA. All good? Well, that introduced another variable, right? Before we had zeros there, but now we have an acceleration. So we have another unknown. Doesn't really change what we have to do, except we're going to have to make sure our expression doesn't have acceleration in it. Or are we looking for acceleration? Perhaps we're solving for the acceleration. Oh, we need an expression for the acceleration. So the problem has changed. We want this. And we can suddenly have this in our answer. Excellent. Still can't have that in our answer, that in our answer, that in our answer. None of that can be in our answer. And we are solving for A. Ready to begin? All right. Choices. I said in the last problem that sometimes it's just easier to get the acceleration. I still stand by that, except this time we're dealing with kinetic friction. Because we're dealing with kinetic friction, there's no reason to sub into the inequality, meaning we can come up with an expression for kinetic friction in terms that we're allowed to have in our answer. First substitution is get rid of that normal force. Then from here, I can plug that in and get a new expression that gets rid of the frictional force. Now, all that's left is to get rid of tension. I think I can do that right there. Add these two equations, get rid of tension. All right, this side, pretty straightforward. Add them together, get the sum of the two masses times A. The left side, the t's are going to cancel out, and I'll get MAG sine theta minus mu k MAG cosine theta minus MBG. I agree. Well, sorry to bore you. Seems like it's going around. You solve that for A? I said that's all that's left. Do you want me to? All right.